let's now move on to our next speaker, who needs no introduction, but I should probably give you one anyway. Professor Tarsanka Debroy from Penn State University, who will be talking about friction stirring of steels.
Thank you very much, Lucy. I want to acknowledge contributions by my co-workers, Professor Amitav De from IIT Bombay and Professor Hari Badesia. Friction stir welding is not commercially used for steels. It's a very nice process for joining of soft alloys like aluminum alloys. And the problem is with the tools for welding of hard alloys, the tools wear out or the tools fail in extreme cases, and the cost of the tools remain high. Also, the problem is added by the high temperature and very rapid heating, cooling, and stresses on the tool. So here is an example of what happens even for hard aluminum alloys like 7000 series aluminum alloys, or if you put in some particles, hard particles, the tools wear out very rapidly, and in extreme cases, for certain conditions, they can even fail catastrophically. So that remains the major problem. And remember that for steels, structure and properties of friction stir welded steels have not been studied adequately. Even for aluminum alloys, the friction stir welding does not seem to have an advantage compared to fusion welding in terms of the strength. So, and remember, aluminum alloys have been studied a great deal more than steels. So even for that, we cannot get properties always as good as that of the fusion standard plain vanilla fusion welding processes. So two issues: insufficient tool durability and high tool cost, issue with the tool, and issue with the structure and properties. They are scarce, they need to be studied a great deal before we can actually commercially use friction stir welding for steels. Thermal history, time temperature history, and the stresses are important for both problems. So the issue is, how do we get the time temperature history, and how do we get the stresses for different welding conditions for friction stir welding of steels? One of the ways in which these types of problems have been addressed in fusion welding is by numerical simulation of heat, mass, and momentum transfer during welding in the fusion zone and in the heat affected zone. So here we take the same approach. We solve equations of conservation of mass, momentum, and energy. We discretize the entire volume of the weld metal into fixed grids, about 250,000 grids, and we are solving for three equations of momentum for three different velocity components. We are solving for pressure, and we are solving for enthalpy. So 5 variables, 250,000 grid points, about 1.25 million equations per iteration, and we do between 5 and 10,000 iterations. So we are solving about 1 billion equations to get to simple things like thermal cycles and stresses on the tool. How long does it take? In an i7 laptop, you are looking at 10 minutes. after 10 minutes, you have a detailed picture of heating, cooling, stresses. Practically anything you want to inquire comes out in 10 minutes. And all right. So to solve these equations, you also need submodels for heat generation rate and viscosity. Just a minute about that. The heat is generated primarily on the shoulder, but also on other surfaces, and to a much lesser extent in the entire volume of the friction stir welding. And we have to have a submodel to estimate heat generation rates spatially at all locations within the domain. And in addition, we also need a model for viscosity. And we get that model for viscosity because we are calculating 3 components of velocity. We can calculate from the velocity strain rate, and we can get a temperature compensated strain rate from the temperature, from the enthalpy equation. And these 3 parameters are material constants for Zener-Holloman parameters, we call them, from hot working literature. So once we get these, we can then calculate the viscosity, so we can solve the Navier-Stokes equation, and we get the entire values. So let me show you what those results look like. First thing is temperature field. And from the temperature field, we can calculate the heating and cooling rates and also time temperature plots. We have done that for a wide variety of materials, ranging from aluminum alloys to stainless steels with very low thermal conductivity, and also titanium 6 aluminum 4 vanadium alloys. So the point here is very different thermal properties and very different mechanical properties. Both are important for these calculations. And in each case, we seem to be able to reproduce the thermal cycles at monitoring locations reasonably accurately. That's the issue. All right. So temperature fields, we can measure temperatures, and we can compare the calculated values with the measured values to see how good the calculations are. Velocities are another question because it's very difficult to measure velocities. So what do? We take a limiting case in which we have analytical solution. That means if you take a rotating plate and you throw in a little pin and you say, okay, I know from experiments what the domain looks like. So I'm going to do an analytical calculation of what the velocity field will look like if I assume that this is simply a viscous flow in which the flow is generated by the movement of the shoulder of the top plate. And then we have got analytical solutions that you can do in the back of the envelope. Okay? Envelope has to be a little big. And then you can compare this analytical solution with what you calculate numerically by solving more than 1 billion equations, yeah, in 10 minutes. And the advantage is you can actually do these calculations very easily. The calculation scheme can be put on a spreadsheet, and the spreadsheet is available in Cambridge University website and also at the website at Penn State, my employer. And they are also described in detail in this paper in Acta Materiala. Apart from velocity and temperature, we can actually measure the force on the tool as the tool moves around. So the traverse force can be computed, and then we can see how good those computations are by measuring it. You can measure it with a standard dynamometer or with a strain gauge or other possible techniques, and they seem to be predicting both the values and the trends reasonably well for different thickness of materials. All right? So temperature, velocity fields, reverse force. The last one we want to compare is torque on the tool. This is important for a reason that will become clear in a moment, but for now we have looked at the variation of torque with welding speed and with rotational speed of the tool, and we seem to be getting pretty good match with independent experimental results. So temperature fields, velocity fields, reverse force, and now the torque. So the point is, if we validate the model, then there is a better probability that the thermal cycles we will use for microstructure prediction and for prediction of maps of tool durability is likely to be little more accurate than if we cannot validate our model. So we have gone as far as we could go with the available results for validating our model, and then we'll be using this. But before I go into the actual field, I want to show you one last view graph on what the model results can be useful, because not everything can be measured. One of the things that cannot be measured very easily is the sticking torque. Sticking torque gives us the grip of the tool on the plasticized material, and that dictates how good the flow pattern is going to be. And we show here that there is an optimum shoulder diameter for each operating condition where the tool's grip on the plasticized material is maximum. And it has been shown that if you go on the left or right, if you do not use an optimized tool shoulder diameter, then there is a good chance you will get a defect in the weld. So structurally sound, reliable welds can be obtained using computer models. 5 minutes? No? Wonderful. I didn't know that it was so popular a lecture, but here we have thermal cycles for the condition that we are going to be looking at the microstructure. Mild steel parameters are here, and we are looking at temperature cycles on the top plane, in the middle plane, and at the bottom plane. And the point here is the cooling rates do not vary all that much, but the temperature at the bottom plane can be about 180 degrees lower than the temperature at the top plane. So in some cases, you may not even form austenite. That's the issue. The cooling rates would not vary a great deal. They will vary, but they will not vary a great deal. Where you can vary the cooling rate is by varying the welding speed, which is like the experience in diffusion welding. If you go much faster, you will cool much faster, that is expected. But here, much faster means only about 20, 30 degrees per second in the 800 to 500 degree range. You are not looking at laser welding where you can cool very, very rapidly. It's not that. And it can be as slow as probably 5 degrees centigrade per second. That's the typical values that we are looking at. In contrast, if you vary the RPM of the tool, the temperature fields do not change a great deal. They do change, but not something to write home about. So if you wanted a different structure, you actually have to vary the welding speed. That's your most potent variable. And it's validated by other people's independent work. Suresh Babu is in the audience. He was on the thesis committee of the student in Ohio State, our neighbor, and they found the same story. So this is not a surprise. Normally, to most of you, it is not a surprise that from cooling rates, composition, and austenite grain size, you predict, you calculate actually microstructure. Many of you have been doing this for a while, so I would tell you that we tried a similar exercise where we consider the driving forces for different phase transformations, and we look at the transformation start temperatures from all these parameters. We consider nucleation and growth of individual phases simultaneously. And then we look at the soft and hard impingement simulation and overall transformation kinetics, and we get microstructure. We did this, and what we found was the most important thing is nothing worked. Nothing worked until we put in a stored energy of about minus 200 joules per mole, all right? About 3.7 joules per gram for steel. And then, of course, we were able to predict the effect of cooling rate, and we expect the grain boundary ferrite, the Widmanstatin ferrite, and perlite. And here is a microstructure that shows exactly that. This is reported in the literature in Welding journal, and we are able to predict qualitatively these microstructures. Quantitatively, we have done some calculations, but it needs to be experimentally validated by detailed quantitative metallography. That work will be done later on. Apart from the microstructure, the other thing that is very, very important is here is our colleague worrying about the tool life, and the value that is important here is very high cost and the durability of the tool. And the tools actually undergo a lot of stress and high temperature. So if we look at the urgent need, the actual need is if we are stuck with a tool and we must do friction stir welding, our goal is to provide guidance for the tool to last as long as it can. And for that, we are developing maps in which we consider the normal stress, the shear stress due to bending, and also due to torsions, and we calculate the resultant maximum shear stress on the tool. And we compare this with the shear strength of the tool. So we take a ratio of the strength of the tool and what it endures in terms of the shear stress, resultant shear stress. If this ratio is large, then the tool will last longer. If we try to weld faster and the heat input per unit length is lower, the temperature is lower, the stresses are higher. So if we vary parameters, the stresses change and the temperature changes, and therefore the tool durability changes. So if we are stuck with a problem, we must weld. Those maps will provide a good guidance as a first step for the tool to last as long as it can. Allow me to show just one view graph and I will stop. And here we show a plot of shoulder diameter versus tool rotational speed, and these solid lines are the strength of the tool divided by the stress that it experiences. So a factor of 10 is good. A factor of 1 or 2 will make anybody nervous because you don't know what will happen. So here, if we go with a lower speed, the safety is higher. If you try to go very fast, there is a chance that the tool will not be very happy. And here again, if you try to weld a thicker plate, then the problem would be a little more difficult than if you weld with a thinner plate. I will stop here. Thank you very much.
Very much for that talk, and thank you in particular for giving a talk on numerical analysis that was not boring, because I know that that's challenging.
Thank you.
Thank you for that. Do we have any questions?
That was a nice talk, but I have a question on mechanism of this friction stir welding. People say there are two type of diffusion mechanism. First is thermal diffusion, other is ballistic diffusion. So in your view, which mechanism is most important for friction stir welding?
You know, the most important diffusion is thermal diffusion, because without heat, there is no welding, even for solid state welding.
That I understand, but in your work you have said that the tool speed has a very strong influence on the microstructure development. So from there it came into my mind that if the tool speed is so important, then there must be some influence of ballistic diffusion in that case.
I am normally very afraid of any type of ballistics, except no, I'm serious. On a more serious this thing, it's a much more ordered process than anything like the type of welding we do with a what do you call that? Explosive welding. The mechanism here is gradual. And that's the reason. I was not trying to make fun out of your question, believe me.
Okay.
Thank you. It's a pretty reasonable question, I think. And I don't completely know the answer to your question.
Just a background question, because I don't know much about this topic. What is that tool actually made of, and is there any possibility for improvement of performance by changing the material of the tool, or is there some constraint that you have to follow with the tool material?
The tool material currently used are polycrystalline boron nitride, and also sometimes tungsten. And just last week, Science and Technology of Welding and Joining actually announced a prize for development of tool. It went to Osaka University's Professor Fuji and his team, and they developed a tool made up of iridium alloys. But you know, iridium is more expensive than gold. And that is what makes me somewhat nervous. Yeah? So there have been reviews by Harry and Rohit Roy and others on tools, tool materials and tools. So they are available in Science and Technology of Welding and Joining.
My question was also about the materials, also about the design of the shape of the tool, if you can comment on that, and also on heat transfer through the back of the weld, because you are pushing stronger. So I guess, and I didn't capture that part of the heat transfer through the box.
Sorry, I was relatively quickly I was passing through that topic. The heat transfer at the back plate is terribly important because it determines the temperature field very, very significantly. You change the heat transfer coefficient at the bottom plate and you will change everything. You will change temperature field, you will change the stresses. And therefore, you will also change the tool durability. Yeah?
So the design of the process is not only on the tool, but also includes the backup materials?
It includes the environment. It also is terribly important to get the right tool shoulder. Yeah? If you go too far from the optimum, you will pay a price in terms of having holes in the weld. People have actually written a complete paper on that itself.
Thank you.
What do you think of the idea of, one approach is to use the tool as a consumable and feed in just more and more and turn what is a problem into a different approach? I mean, do you think that's got any legs?
It is a consumable to the extent that tool materials get embedded in the weld and can develop that with appropriate additions so that the weld metal would be a composite metal deliberately created and structured. That would be an exciting idea, but for now, welding community is very conservative and we are more nervous and less hopeful about that particular issue. Would you like to add any comment to that?
I think the tool materials are the wrong sort of materials to put inside steel. But in principle, a consumable tool using a steel would be okay.
I think for spot welding, if you can have a tool of composition very close to the composition of the final product, you won't leave a hole, and the automotive industry would be very, very excited about your work.
It's not my work, it's just an idea.
Your idea, sorry, I misspoke.
I just want to add that it's actually a GE patent which is for consumable friction stir welding too. So there's one of the problems with friction stir welding, as you all know. You stumble on every other patents every other time. So it's one of the developed by GE on that.
So thank you, Suresh. That's a valuable comment.
I have another question on the transitions. So you have to start and you start to finish. That's my question. So is this something you work on, how to make the transition faster or shorter, considering that part of the product will probably not be useful?
It is more useful for the transient processes, like the spot welding. Here we have focused mostly on steady-state processes, so this particular talk was not focused on that, and we have not worked on that important problem.
Thank you.
The problem with the tool is that because of the very high temperatures that you're using, or is it, would that happen at any temperature? Because there were some Japanese experiments done some 5-6 years ago where they welded at like 700-800 degrees centigrade. Would that help to prolong the life of the tool?
The problem with the tool is both temperature and severe stresses in a condition of very high strain rate. The actual mechanism for degradation ranges from chemical degradation, in which there is reaction and disintegration of the surface of the tool getting embedded in the tool material, to erosion of the surface, and in extreme cases, breakup. So you will have a whole range of problems with the tool, depending on the specific material and welding conditions.
Okay, and
I'm sorry, this is a general answer, but
yeah, and we've got one question from the internet.
I'm not sure the question is relevant, but it's a question from Rashid Bhakti. Have you seen any difference in terms of life between tungsten radium and PCB, and I think it's polycubic boronitride 2 material?
we have not compared it except for a review in which we have looked at the general suitability and the advantages and disadvantages of the use of those tool materials. They are available in details in Science and Technology of Welding and Joining in a review that says review on the review. Okay. Thank you.
Meta review. All right, that's all we have time for questions. Thank you very much for that talk.
Thank you.
It was really interesting.